The basics of the camera. The lens. Recapping from lessons 1 and 2, which can be found at the links below the view pane, there are 3 basic parts of the camera, and everything else is just an enhancement to the 3 basic parts, which are light, lens, and recording media. In this lesson, we will take a basic look at the lens. The name lens comes from the lentil seed because of the shape of the legume. Although lenses come in a wide variety of shapes and sizes, the basic shape of a lens is that of a lentil seed. In Lesson 1, the pinhole camera was introduced, and much will be said about it in future lessons. The lens in the pinhole camera was just a tiny hole that will not gather much light, but focuses the light on the image plane rather nicely. The stream of light through the pinhole was always in focus, no matter how far away the image plane was. When a glass lens is introduced, it gathers more light as the hole is now larger. But the light is not always in focus, so there is a trade-off, and the simple lens or hole of the pinhole camera is made a bit more complex by adding a larger hole and a glass lens. The size of the hole, not the lens, is called the aperture. The aperture is an enhancement to the lens. The camera lens can be very large, but blocked off by a device called an aperture. By adjusting the aperture to be smaller and smaller, one gets closer and closer to the size of a pinhole. You will recall that a pinhole is always in focus. Now let's take a look at what happens when more and more light is allowed through a larger and larger hole, or lens and aperture combination. A pinhole lens does not allow much light to get through to the recording media, but it is always in focus. A large glass lens with a large aperture opening allows a great deal of light in, but there's a limited area of focus. This limited area of focus can be manipulated by the skilled photographer to make some amazing photographs. The photographer can bring into focus what he or she wants you to notice in the photograph. Let's take a look at a few examples. The name of this limited range of focus is called depth of field. With a large lens and a large aperture opening, things up close are out of focus and things far away are out of focus too, but there is a middle ground where things are in sharp, clear focus. Lenses have been around for thousands of years. At first, they were called magnifying stones and were polished clear stones. It was not until about 1,000 years ago that the science types started to fool around with glass and stones to make better and better lenses. Then, about 500 years ago, things with lenses really started to take advance. A Dutch fellow claimed that he had invented a device that allowed him to see objects at a distance, but up close. We know this today as the telescope. Then, Antoine van Leeuwenhoek invented the microscope so that he could see really small things better. Soon, another science type turned the telescope to the night sky, and Galileo forever changed the way that we look at ourselves. This happens every time we invent a new telescope, too. Lenses work by bending light. Bending light is called refracting the light, but no matter what it's called, it's just bending the light. Just how it is that it bends the light is way beyond the scope of this lesson. Here, you see some colored laser lights passing through a series of different lenses, and you can see how the light is bent or refracted. You can easily prove to yourself that this refracting thing happens by simply filling a clear glass with water, sticking in something that is straight, which could be your finger, and you will see that it looks like it is bent. When Ernest Rutherford was a boy in New Zealand in the 1880s, he amazed himself by sticking sticks into the water and seeing how much they looked like they were bent, but they were not. When he accepted the Nobel Prize in 1908, he recalled how this simple phenomena set him on the course of science. Many natural or common things can bend light. A glass of water sitting on the windowsill can bend the sun's light such that it can accidentally start a fire. A makeup mirror can easily bend or focus the light such that it too can cause a fire. A bottle of water can focus the light such that it catches the grass on fire.
Normally, we'd think of using water to put out a fire. We'll need to remove the label from this little bottle and use the convex edge as a makeshift magnifying glass to focus the sunlight. It only takes a few seconds to get this paper smoking, and pretty soon, we've got it smoldering. When the hole is about the size of a quarter, we'll need to slowly add multiple layers of papers. Swinging it around gently will help the air get to the embers, and when they get hot enough, a flame appears.
When Isaac Newton was a boy and was sent home to escape the plague, he came up with many things. One was a better way of making a telescope. Rather than have the light collected with a large lens, his telescope would capture the light with a large mirror and then focus it onto a lens and then project it to some sort of recording media. In Newton's time, that recording media was the retina of the eye, and the image that was recorded is called a memory. Though Newton's design, called a Newtonian telescope, is several hundred years old, it is still the design that we use today to capture light with our largest telescopes, both on Earth and with our space telescopes.
If you look at a scene through a single lens, it appears upside down. Why is that? Lenses that are thicker at the middle are called convex lenses. These lenses cause parallel light rays to converge to a single point, called the focal point. When light rays pass through the lens, they do not travel in straight lines, but rather bend slightly inward. This phenomenon is called refraction. When light rays pass through the lens, they refract and converge to a single point to produce an image. Because the image passes through the lens to the opposite side, it is projected upside down. This process alone, however, is not enough to produce a sharp image. This is because, strictly speaking, a spherical convex lens alone cannot cause light to converge to a single point. The focal point where light rays passing through the center of the lens converge differs slightly from the focal point where light rays passing through the edge of the lens converge. This is called spherical aberration. In addition, color fringing may occur. This is called chromatic aberration. When light passes through a convex lens, the focal point for red light, which has a long wavelength, is farther away from the lens than the focal point for blue light, which has a short wavelength. This causes colors to shift. As a result, colors appear to bleed. Making light converge neatly to a single point requires technology. Since the direction in which spherical aberration occurs in a convex lens is opposite to a concave lens, through a combination of two or more lenses, light rays can be made to converge to a single point. This is called aberration correction. Chromatic aberration can also be corrected by combining two lenses. To achieve the most beautiful images possible, actual camera lenses incorporate multiple individual lenses that correct focus and color bleeding. Lenses for single-lens reflex cameras are made up of a large number of lenses. Each lens is responsible for such roles as adjusting colors, distortion, and focus, as well as changing the focal distance.
This concludes the intro lesson to the basics of the camera, the lens. You should be able to answer the following questions on a separate sheet of paper. Please write the questions and your well-written answers to each of the following questions.